Uh-huh.
So we finished all of the alkenes.
Yes.
Okay, and then
Alkynes and alcohols. More alcohols than alkynes. Correct.
for the
Possibly. It kind of just depends on how the question is phrased. If you may, well, you will definitely have a mechanism type problem on the exam four and the final. But if you are, yeah, I mean, there's multiple ways you can be tested on those on the knowledge of the reaction. You could be asked for a mechanism, but it would say clearly write the mechanism of this reaction. Um, it could be a predict the product type thing, like your quiz is going to be, or it could be as a synthesis type problem. And we haven't really gotten into those. That's where we're going in very short order. In fact, the homework two is going to get you some practice with this idea of synthesis. And I'll talk to you about that a little bit more tonight in lab. Okay. Okay. So, what I wanted to do, I know I talked about this a little bit in the intro video, but I think it's really important. And so I want to spend a little bit of time talking about it here just to kind of reiterate some things. We've already talked about the alkanes and the alkenes. Now we are moving to the alkynes, and they have something unique about them that was not an issue, was not relevant when were talking about the alkanes and the alkenes. And that is the fact that they are reasonably acidic. Okay. When it comes to acid base chemistry, everything is relative. So when I say the alkyne is reasonably acidic, I'm not saying that it's like a strong acid by any stretch of the imagination. It's not even what most people would consider a weak acid, but it is somewhat acidic. Okay. So let me give you some numbers. The pKa of an alkane CH is so high, it's really difficult to even measure accurately. You're talking about in the neighborhood of like 50 to 60. We'll just say 50-ish. Um, the alkene, it's actually a little, let's say more like 60-ish. The alkene CH is somewhere in the mid 40s. Again, so high, it's difficult to get an accurate measurement. The alkyne is down at 25. So again, that's not very acidic. I mean, you consider even a weak acid like acetic acid, the pKa of that is like 4.8. So that's nowhere near the acidity of even a weak acid. But that said, we have bases that can deprotonate that. Now, I think it's important to understand this trend. Why is it that the alkyne is more acidic than the alkene, which is more acidic than the alkane? What that has to do with is something we've talked about before, and that is in the so-called S character. Remember, an alkane, the carbons are sp3 hybridized, the alkene, the carbons are sp2 hybridized, and the alkyne, the carbons are sp hybridized. So in terms of that S character, the alkane is 25% S, the alkene 33% S, and the alkyne 50% S. Now, it's important to remember what that actually means. When we talk about something having S character, what that means is that it's close to the nucleus, it's close to the nuclear attraction. And so having more S character provides greater stabilization to a negative charge. Right? I mean, you think about if you're going to deprotonate that, you are going to form a negatively charged so-called acetylide ion. Right? If I deprotonate this thing, you're going to end up forming something that looks like that. Well, and I mean, really, deprotonate any of those, alkane, alkene, or alkyne, you're going to make some C minus species. Well, the more S character you have, the closer that negative charge is to the nucleus, the more stabilized it is. And so having more S character makes that a more stable anion. And I mean, not surprisingly, the more stable and something is, the more likely it is to form. So that's kind of what explains this trend in acidity. Right? Again, the more stable something is, the more likely it is to form. All right. So I have a couple of different acid-base expressions written for you. I want you to consider the scenarios. I have this compound here, this 2-carbon alkyne. IUPAC would call it ethyne. It's more commonly known as acetylene. But what I have here is acetylene, and we're trying to deprotonate it with a base hydroxide. Now, in order to predict which way this equilibrium is going to be favored, we need to know the pKa values of the acids. All right. I just told you a minute ago, the pKa of the terminal alkyne is 25. Now, the other acid in this expression would be the conjugate acid. In this case, would be the water. All right, that is the acid in the reverse direction. So the pKa of water is 15.7. So on the basis of having known the two pKa values, we can predict the equilibrium. All right. There's a couple ways of thinking about this, so do it whatever makes sense to you. The way I always think of it is I look at those two pKa values and I say, okay, well, what's the stronger acid? Stronger acid is smaller pKa. So the stronger acid in this case is water. Well, if water is a stronger acid, that means it will be more likely to exist without its proton. Well, there's water without its proton. So this would be a reactant favored equilibrium. Meaning, if I took the acetylene and treat it with hydroxide, you're basically not going to make any of that. This is reactant favored. Saying it another way, hydroxide is not a strong enough base to deprotonate acetylene. So let's look at another example. The exact same thing. The only thing I'm trading out is the base. So here, instead of using hydroxide as base, I'm using the NH2 minus species. So again, to get some insight into where the equilibrium lies here, we need to know the pKa values. Well, that's the same terminal alkyne, so its pKa does not change, it's 25. The conjugate acid here is ammonia. Ammonia has a pKa of about 38. That changes everything. I'm looking at this and I'm comparing the acids. Well, now it's the alkyne that is a much stronger acid. If it is a much stronger acid, it will be the one more likely to exist without its proton. Well, there it is. There's the alkyne without its proton. So this process would be a product favored equilibrium. So what that's saying is that NH2 minus is a strong enough base that it can easily deprotonate the alkyne and generate this ion here. This is what is known as the acetylide ion. And that's what we're going to be doing, where we're going to be dealing with for the first couple of reactions of the alkynes. We're going to be looking at deprotonating the terminal alkyne and then using the acetylide ion for stuff. All right, so let's have a look at it. This is exactly what I just showed you. Sometimes it's easier to see or deal with these alkynes if you actually draw in the carbons. So on the slide here, I have a 1, 2, 3 carbon alkyne. And as you can see, you're using that NH2 minus. That base there is what's known as sodium amide. So that is the most common base to deprotonate these terminal alkynes is the sodium amide base. Sodium hydride can also be used, but it's much more common to use the NaNH2. And as you can see, what that generates is that 3-carbon acetylide. All right. Now let's see what you can do with it once you make it. The acetylide is a very strong nucleophile. All right. So we can use it as such. That's what this reaction is showing you. So you can see that in the first step, they are going to take the proton from that 3-carbon alkyne, going to generate that acetylide. And then we're going to use that as a nucleophile in an SN2 type reaction. So you could imagine, I'm going to, instead of using generic RX, what if I gave you bromoethane? Well, this is just going to do an SN2 as the nucleophile attacks the good substrate. And so the product that would result here would end up looking like, so there's the 3-carbon acetylide, and it is now just going to attack the 2-carbon alkyl halide. So we would end up getting that as a product. So the 2-carbon group from the alkyl halide just ends up on the nucleophilic carbon. Now, what's important to note here is that it is, in fact, an SN2 mechanism. And because it is an SN2 mechanism, you have to be careful about what kind of substrate you use. Remember, SN2 is very sensitive to steric. So you're never going to get this to work on like a tertiary alkyl halide. Right? Because this is an SN2 mechanism, you're only going to be able to do this with methyl or primary alkyl halide. Look, let's explore why that would be. So you can see I'm, in this example, trying to react the acetylide ion with a secondary alkyl halide. So presumably what we're trying to get here is we're trying to stick that acetylide species onto the ring. Like that. That would be the SN2 product. What's the problem with the reaction as I've drawn it? Why wouldn't this be the major product? With those more hindered substrates, the secondary and certainly the tertiary, they do not undergo, well, the secondary could, But what would be more favored with the secondary and certainly the tertiary is instead of having SN2, remember that acetylide is, yes, it is a strong nucleophile, but it's also a very strong base. And so what is more likely to happen with the secondary and exclusively with the tertiary is we're going to deprotonate and kick that out and make the E2 product. And that would be the major. So that's why I say, if you're going to try to do this chemistry, use the acetylide as a nucleophile in an SN2 type mechanism, you have to make sure that your substrate is amenable to that, meaning methyl or primary alkyl halide. All right. Questions there? Okay, let's see what else you can do. The acetylide can also, remember the acetylide is literally just a carbanion. And so you'll recall experiment 11 parts BC, we used a Grignard reagent, which was like a carbanion, and we used that to attack carbonyl, specifically acetone. Well, you can do the exact same thing with this carbanion nucleophile. You can use the acetylide to attack carbonyl. And it happens the same way that we saw with the Grignard. You know, if you were to make the acetylide of this guy again, well, remember the carbonyl carbon is delta plus. Right? Because I can draw that resonance form of any carbonyl compound. Any carbonyl compound has a resonance form that looks like this. There is a partial positive charge on the carbonyl carbon. And as a result, nucleophiles are attracted to it. And so this acetylide species is going to go in and attack that carbonyl carbon. Well, as it does so, I can't just stick the acetylide on that carbon and leave everything else as is, because then that carbon would have 5 bonds. So as the acetylide comes in to attack, one of the existing bonds breaks, and it will be the pi bond because that is the weakest of the bonds. So your intermediate there is going to look like this. So kind of color coded it there. The black represents the acetylide species. The blue represents the carbonyl species. You'll notice that we end up with this charged intermediate. And it was the same thing when we did the Grignard reaction in lab. And so just like when you did the Grignard reaction, you had to pour it into acid to give this thing a proton. You have to do the exact same thing with these acetylide reactions. In order to isolate a neutral organic molecule, I need to protonate that O minus. And so that is why I have this H3O plus step, right down here, right down there. That H3O plus step is to provide this O minus, its proton, so you can isolate that neutral organic molecule. All right, so this was the reaction with the 1-carbon aldehyde. This is called formaldehyde. All right, could you predict the product here? Taking the acetylide, or forming the acetylide in step 1, adding the acetylide to the 2-carbon aldehyde. could you predict the product of that reaction? All right. So we formed in this case, the 4-carbon acetylide. We added it to the 2-carbon aldehyde, and we should get a structure like this. You're gonna color coded it. The black is from the acetylide, the blue is from the aldehyde. And so that thing would just hang around until you pour it in acid. Mhm. Um, from the top example, the NH2 to act as a base and grab a proton from where? Oh, to grab an H from here? Oh, because the NH2 minus had already been used by that point. Right. That's why I have them in steps. Like you're the what that indicates when you see the step 1, step 2, step 3, it means that you're not just taking all of this and throwing it all in the flask together. You're doing it stepwise. So the first thing that we would be doing is taking the acetylide and adding NaNH2 to it. At that point, all of the NH2 minus is gone, right? It has all been used to make that acetylide nucleophile. And so then once you've given it a few minutes for the deprotonation to occur, then you would add in the aldehyde. And then the only two things you really have in the flask at that point are the nucleophilic acetylide and the electrophilic aldehyde. And so they would react with one another. And so then there's really nothing else in the flask. So that's why I say that thing is just going to kind of hang out until at which point you then add the acid to it to protonate. Yeah, all of that NH2 minus would have already been consumed making the acetylide. There's no more NH2 minus left to grab a proton from this. And by the way, that would not be an acidic proton anyway. Because imagine if you were to deprotonate that, that would put a negative charge on that carbon. So you'd have a C minus right next door to an O minus, which would be incredibly unfavorable. Okay. Good question though. Okay, so then, any questions on how we got to this product? Okay. Oh, by the way, one tip I will give you as we're starting to do these what I call chain growth reactions, like growing the carbon chain, I would strongly recommend getting in the habit of counting carbon. It will help you avoid making silly mistakes. What I mean by that is I am starting with a 1, 2, 3, a 4-carbon chain. I'm adding it to a 2-carbon chain. Well, that's math I can actually do. 4 plus 2 is 6. So I better end up with a product that has 6 carbon. 1, 2, 3, 4, 5, 6. We're good. All right. Okay. I can also add this to ketones. So could you predict the product of this reaction? So still, again, kind of the same old story, making the acetylide. Only difference is this time we're adding it to a ketone instead of an aldehyde. All right, so that NaNH2 is going to deprotonate and make the acetylide. And that will then add to the carbonyl of the ketone in this case. So here again, I've color coded it. The black is from the acetylide, the blue is from the ketone. I would get that alkoxide intermediate, and that thing would hang out until we acidify. All right, and so again, you can count your carbons to make sure we didn't make a mistake. I'm starting with a 3-carbon chunk, and I'm adding it to another 3-carbon ketone. And so 3 plus 3 is 6. Our product should have 6 carbons. 1, 2, 3, 4, 5, 6. We're good. All right. Oh, yeah. Yeah, it's same thing. Yeah, H plus is just kind of a lazy man's way of writing H3O plus. Yeah. Um, and you'll see it both ways, just depending on the book or the person who's writing it. But they mean the exact same thing. Okay, so that is a way of making alkynes. We can add terminal alkynes in the form of an acetylide to either alkyl halides or carbonyls. All right, now I want to show you a couple other ways. The other way you can synthesize alkynes is through a double dehydrohalogenation. Now, as we move forward for the rest of today's lecture, what I would encourage you to keep in mind are all those reactions of alkenes, because they will pretty much one for one apply to the alkynes as well. I mean, remember, the whole reactivity of the alkene came from having the pi electrons go and attack something. Well, an alkyne is very, very similar to an alkene. It's just that we have 2 pi bonds now. And so generally speaking, all those reactions of alkenes that you learned or in the process of learning, you're going to see for alkynes. It just happens twice because we have 2 pi bonds now instead of 1. Mm-hmm. Mm-hmm. It's no, probably the reaction is more important. Okay, so what I'm showing you here is we have 2 different types of dihalide. On the left, we've got what's called a geminal dihalide, where the halogens, represented here by those X groups, are on the same carbon. And then on the right, we have the vicinal dihalide, where they're on adjacent carbons. So we can do this reaction in the 2 ways shown. Let me go ahead and give you an actual structure. So we have that geminal dibromo compound there. And the way this reaction is going to work is you would have some strong base, and it's going to go in and grab the proton, electrons flow in, and kick out the halogen leaving group. So that would result in an alkene. Right? I did one elimination, and so I got one pi bond. Well, you still have an H, you still have a halogen. So this process happens a second time. Base is going to come in, grab that one, electrons flow in, and kick out the other halogen. And so in the end, we make the terminal alkyne. Now you could possibly see how the vicinal version would work. Right? So if we were trying to work with a vicinal dihalide, it would look like this. So here again, strong base. After the first elimination, I make one pi bond. Well, here again, I still have an H and I still have a halide. So this happens a second time. All right, now, as you can see, we can make through this chemistry, through this double dehydrohalogenation of the dihalo compound, you can make either a terminal alkyne or you can make the internal alkyne. And it largely depends on the base you use. All right, so have a look at this example. In this method, the base that's being used is molten KOH. Now think about that for a second. KOH is just a salt, kind of very similar to sodium hydroxide. So I don't know if you've ever worked with sodium hydroxide before, but it's little pellets, kind of white pellets. When it says molten like that, it's not just like a 10% solution of hydroxide. All right, it's not taking some hydroxide, putting it in water, and then adding it to your dihalo. It's molten, meaning it's liquefied, meaning like if you want to, you have to melt it, right? Well, salts, as it turns out, have very, very high melting points, as you can see in the 200 degrees Celsius range. So you have to put that potassium hydroxide, that salt, in a vessel and superheat it, like over 200 degrees or more, to liquefy it. And then you add your dihalo compound into it. So this will work, and it will provide for the internal alkyne because it is a more thermodynamically stable product, kind of like alkene stability. The more substituted the alkene was, the more stable it was. Same thing holds for the alkyne. So that's why it's a more stable product to have an internal alkyne than a terminal. But you do have to be careful here because that liquid 200-degree KOH is going to wreck a lot of functionality. There is a lot of functional groups that would not survive those conditions. So it's not like really a universal thing. If you had any other kind of like esters or anything like that, they would not survive this condition. So you do have to be a little bit careful with that. But the other way of doing this, so if you want the internal alkyne, you use KOH at 200 degrees. If you want the terminal alkyne, you're going to use a different base. You use the NaNH2 here. And that will ensure that you get the terminal alkyne. And the reason for that is because that's not technically your product. Usually the way this is done is you actually use 3 equivalents of the base. You need you need 2 equivalents of the base to take off 2 of the protons here. And then the third equivalent is going to actually deprotonate your terminal alkyne that you make. That's what kind of drives this equilibrium to the terminal. You know, I mean, in theory, you could make internal or terminal, right? The NaNH2 is a strong enough base to deprotonate anywhere next to the halogen. However, because as soon as you make the terminal, it gets deprotonated, that kind of pulls that thing out of the equilibrium. And according to Le Chatelier, if you're removing a product from the equilibrium is going to shift to make more of it. So that's why you see that step 2 is water. That water is going to serve to give the H back to the acetylides that you make. The bottom line is, the take-home message of this story is, if you want an internal alkyne, use KOH. If you want a terminal alkyne, use NaNH2. All right. Questions there? All right, let's go ahead and look at hydrohal. Yeah, go ahead. Uh-huh. Mm-hmm. It's just another term for it. Yeah, you'll see both used. Molten is the same as fused. It just means liquid. Okay, so as I said a minute ago, a lot of those same reactions that you saw for alkenes, you're going to see for alkynes. It just happens twice, all right? Like hydrohalogenation. So you remember, we were able to add HX to alkenes. You can do the same for alkynes. And mechanistically, it will be identical. So in the first step, the pi electrons are going to go out and grab the H plus. Let's say we're using HBr. Now, in theory, that H could add to either of the triple bond carbons. Right? If it adds to the terminal carbon, you get that cation. If it adds to the internal carbon, you get that cation. Do you see why one of these would be favored over the other? Yeah, which one is more stable? Yeah, because that's a secondary type carbon, that's a primary type carbon. The exact same thing we saw with the alkene. So in fact, we don't see that. So you have this carbocation, and then the bromide or whichever halogen you're using would come in and attack. Giving you the alkene. Well, we already saw if you have an alkene in the presence of HX, the pi electrons are going to go and attack it. So this just happens a second time. And then the Br minus will just attack a second time. And so you end up with a dihalide. And just like we saw with alkenes, if you add HX to an alkene, you got Markovnikov addition of the bromide, of the halide. Same thing holds here. If you add HX to an alkyne, you get Markovnikov addition of the halide. Mm-hmm. Yeah, I mean, rearrangements aren't really going to, I mean, I guess in theory, you could have rearrangement at this stage, but you don't usually see that very often. Okay, now if you remember when we were talking about alkenes, we said there was a way to add HX Markovnikov. There was also a way to add it anti-Markovnikov. Same thing holds for alkyne. We can do this reaction in the presence of peroxide and get the other addition product, right? The way this is going to occur is, remember the peroxide, all that's going to do, all the peroxide does is it makes the bromine radical. And so here again, we could have this react in one of two ways. I could put the bromine there, which puts the radical there, or I could put the bromine there, which puts the radical there. Well, radical stability is the same as carbocation stability. The more substituted the radical, the more stable the radical. So this is not going to form. So at this point, you have hydrogen radical in here as well. And this just happens one more time. So again, just as it was with alkene, if you do HBr addition in the presence of peroxide, you end up getting the anti-Markovnikov product. All right, questions here? Yeah. We're starting with the alkyne. Oh, so one of the pi bonds is breaking, doing like a homolytic cleavage. One of the pi electrons here is going to react with the bromine radical, and then the other one is just going with the carbon. So that's why we lost one of the pi bonds. This carbon grabbed the bromine and it put the radical on that carbon. Well, the above it was not a radical reaction. It was both of the electrons of the pi bond went to attack the H plus. So that's why the H ended up over here, and this carbon ended up electron deficient because both of the electrons were taken from it. Yeah, the difference between a polar mechanism compared to a radical mechanism. Okay, next reaction, we learned this one with alkenes too. You can halogenate. Not surprisingly, we're going to do this the same way. It's just going to happen twice. So mechanistically, the way this works, let's see, we're going to do bromine as an example. Remember, this mechanism goes through that three-membered ring. The so-called bromonium ion. And then the Br minus that's still in solution here is going to go in and attack. And then it just happens again. Pi electrons of the alkene will go and attack another molecule of bromine. Makes another bromonium species. And then that remaining Br minus comes into attack. And we end up with a tetrabromo compound. It's not going to make a difference because everything's all the same, right? Because I mean, because those two things are identical, that is not a chiral carbon. So you're not going to be able to tell the difference which bromine came from which molecule at that point. It's just all going to look like bromine. Mm-hmm.
And the first eyeball that was.
Mm-hmm. Yep.
And then there's another.
Uh-huh. Yeah. The exact same thing. Just happens two times because we've got two pi bonds. This one, you're honestly not going to use this very often. It's like, I don't know why in the world you would ever want a tetrahalide compound, but the next reaction you will use quite extensively. This is something else we saw back in the alkene chapter. This was catalytic hydrogenation. So if you recall, when we did catalytic hydrogenation of alkenes, it was really quite simple. H2 just added across the double bond. Well, here's the same thing, only you have two pi bonds. So if you take your alkyne and treat it with H2 and one of the transition metals, in the same way that I encourage you just to redraw the starting material without pi bonds, you will do the same thing here. So if I were doing this reaction, Notice I've got a 1, 2, 3, 4, 5 carbon alkyne. Treating it with H2 and palladium or H2 and platinum, whatever. I'm just going to redraw that starting material without the pi bond. So the alkyne gets reduced to the alkane. Very straightforward. Now, there is a way to get to the alkene and stop. In fact, there's a way of getting both a cis alkene or a trans alkene, depending on what you want. So if you're trying to get to the cis alkene product, you're going to use catalytic hydrogenation. It's the only difference is in the catalyst. What they use to stop at the alkene is they use what's called a poisoned catalyst. And this poisoning agent, there's a few of them that can be used. Sometimes they'll throw in some lead compounds. You can see this one uses a barium compound with quinoline. You can use nickel boride. There's a bunch of different things that can quote unquote poison a catalyst. But what that means is it just reduces the activity of the catalyst. So if you remember, when we talked about catalytic hydrogenation in the previous chapter, we said that the catalyst was just providing a surface for the hydrogen to adsorb onto. And then when the pi bond got down close to it, those hydrogens, it was almost like something sitting down on a bed of nails. Those hydrogens are going to add to the same face of the molecule. So your product here, because those H's added to the same face, they add cis to each other. And because the H's add cis to each other, that forces the carbon groups to be cis to each other. So because of the nature of the catalytic hydrogenation, because of the thin addition of it, it gives you the cis alkene if you use this poison catalyst. By the way, the most common poison catalyst that they use is this thing called Lindlar's catalyst. So most of the time when people want to use a poison catalyst, they don't actually write out H2 with palladium, barium sulfate, methanol, and quinoline. Instead, what they'll do is they'll just simply write H2 Lindlar. And everybody knows that's a poison catalyst. All right. So you can reduce the alkyne all the way to the alkane if you want. Or as we've just seen now, you can take the alkyne and reduce to the cis alkene. Or you can do it a third way to get to the trans alkene. And this involves a completely different type of reaction. This is going to use what is known as a dissolving metal reduction. They're really kind of cool reactions. You can see what we're doing here is you're going to use some alkali metal, so sodium or lithium most commonly. And the solvent here is kind of a weird one. It's ammonia, which ammonia is a gas at room temperature. So the way you have to do this, so most or a lot of schools, a lot of research groups will have an ammonia tank. Again, it's a gas at room temperature, so you have to have a tank of it. But in order to get it in a liquid form, they'll run it into, kind of run a line into your round bottom flask. But in order to condense it, to liquefy it, it has to get super cold. So you put that round bottom flask in a dry ice acetone bath. So the dry ice has a temperature of -78. So as that gaseous ammonia gets into the round bottom flask that is cooled to that temperature, it liquefies the ammonia. Once you have the liquid ammonia in there, you add in the alkali metal, and it's really quite impressive. As soon as you do that, everything turns brilliant blue. And the reason for that is what you are making is, remember those alkali metals have a single valence electron that is really not held very tightly. As if you remember from Gen Chem, the alkali metals have a fairly low ionization energy, meaning it gives up that electron very easily. So as it enters, as you put that alkali metal into the ammonia, what ends up happening is that electron gets given away to the solvent. All of that ammonia forms kind of a cage around the electron. This is what we refer to as a solvated electron. And the reason is, remember all of those H's of ammonia are delta plus, because that NH bond is polarized. So that electron, the negative charge of the electron, is stabilized by all those delta positives of the ammonia. But that is what ultimately adds to the pi system of the alkyne. So one electron is going to add, and it's going to cause those pi electrons to move over to the other carbon. So you end up making something that looks like this. So you have a radical there and a negative charge there, this radical anion species. Now, this is not a favorable conformation for that radical anion because it has all of that electron density right next to each other. And so what is a much more favorable way for those electrons to be disposed is like that. It gets those electrons away from each other. And so that negatively charged group of electrons is going to grab a proton from the ammonia. And then another solvated electron will add to pair up with the radical. And then that one grabs a proton from solvent. But the end result is a trans alkene. Now, by the way, I'm never going to ask you this mechanism. I'm just trying to explain why it is this gives you the trans alkene. You don't necessarily need to know that. All you really need to know is H2 in Lindlar's gives you the cis alkene. The dissolving metal reduction gives you the trans alkene. All right, questions there? All right, so here's how an exam problem might work. Got a compound here. and we're going to take it and reduce it in a variety of ways. Your job is to give the product of each. Now, the easiest one here is the arrow going to the right. All right, that's just regular old catalytic hydrogenation. You literally just have to redraw the starting material without any pi bonds in it. That would be the answer. All right, let's do the dissolving metal reduction. Well, remember, the dissolving metal reduction will take the alkyne and partially reduce it to the trans alkene. So what I did, my alkyne is now a trans alkene here. Is this the correct product? Bless you. There's something missing, I think. What am I missing in that product? Yeah, the double bonds in the ring. The dissolving metal reduction is not going to do anything to double bonds. The only thing that that'll do is partially reduce the alkyne. So it's not those double bonds that are present in the starting material are going to be completely unaffected. All right, what about the Lindlar's version of this? Not it. All right. So remember that hydrogenation with a poison catalyst is going to result in the alkyne being partially reduced to the cis alkene. Do I need double bonds in the ring here? Yeah, I do. I mean, if the hydrogenation were going to affect double bonds, well then I wouldn't have this one. So yeah, I need to include those double bonds. All right, questions here? Okay. Well, here's a good one. This will kind of get you. So this is kind of like your homework number 2. So see if you can come up with a way of taking this and making this mixture of products. Now, this is going to require more than one step. So the first thing to notice here is your starting material has 3 carbons and your products have 6. So that means we've got to grow our chain. How do you want to do that? Kind of the first order of business. Anybody know any good ways of taking a terminal alkyne and growing a chain? I think we saw that at the very beginning of today. All right, I can take that terminal alkyne, deprotonate it with NaNH2. We've got 3 carbons already, but we want 6. So that means I need to add a 3-carbon chain to it. So probably easiest just to use something like bromopropane. That would end up giving you that. Okay. So we're obviously not done. Number one, we don't have the bromine present, and we've got a triple bond here that's not in the product. So can I just add HBr here? No, because if you add HBr to an alkyne, it's going to add twice. You'd end up with a dibromo compound. So what do you want to do? How do you get the bromine to just add one? Well, the reason why bromine would add twice if we were just to add HBr at this point is because there are 2 pi bonds. So if you only want bromine to add once, you need 1 pi bond. So how do we do that? How do we get rid of one of the pi bonds here? Doesn't really matter. I mean, we're going to do one of those partial hydrogenations. So either H2 with Lindlar or the dissolving metal. It really doesn't make a difference in this case. So now we've gotten rid of one of the pi bonds. Now we can add HBr. You see why I draw both of the product here? Because these carbons are equally substituted. If you put the H here, that puts the positive charge on that carbon, which would be a secondary carbocation. If I put the H over here, that puts the positive charge there, which is also a secondary carbocation. There's no preference for either one. So you would get both. All right. Questions there? Okay. This is where we will end today. This is the hydration. So this is yet another example of a reaction we already learned with alkenes that we are going to apply to the alkynes. So if you recall with hydration, we talked about a couple of different ways of doing it. There was the mercury method and there was the boron method. Same thing holds here. The first way we're going to do this is a mercuration. And again, just think about the reaction and the mechanism that you already learned and just apply it to this. It's the same. All right. In the same way that the pi electrons attack the mercury back in the previous chapter, same thing happens here. In the same way you made that 3-membered mercurinium ion back then, do the same thing here. And I can make the same argument about the distribution of charge in this mercurinium. There's going to be more positive charge at the more substituted carbon position. And so when the water comes in, it will be more attracted to the larger positive charge. So you end up getting that. Problem with this is that this is what is known as an enol. You got an alkene, and directly on the double bond is the alcohol. So an enol. Enols are really unfavored, and they will only exist as a probably 0.01% of a sample. They will largely undergo a specific type of rearrangement known as a tautomerization. Mhm. It just kind of dissipates, kind of falls off the molecule in this situation because it's on a sp2. In the alkene version of this rather, we had to use the sodium borohydride to get rid of it because it's on an sp2 carbon. It's a lot less stable, and so it just kind of falls off the molecule in this reaction. Um, but this rearrangement will occur because it's better to have a carbon oxygen double bond than a carbon carbon double bond. And so you end up after this rearrangement with that as a product. So you end up making this ketone product. Now with the boron version, again, the mechanism is quite similar. So when the BH3 comes in to react, it ends up interacting like that. Just due to sterics, the BH2 is going to prefer to be on the left substituted carbon. So that little tiny H ends up at the more sterically hindered congested carbon. And then whenever you treat this with the basic peroxide, here again, all that's going to do is replace the boron with an OH. Well, that is also an enol. And that will also tautomerize. So in the case of the boron reagent, the oxygen ends up at the left substituted. So we say it's anti-Markovnikov with a oxymercuration. The oxygen group ends up at the more substituted carbon. So it is Markovnikov. Oxymercuration gives you ketones. Hydroboration gives you aldehyde. All right, so I think that's enough for tonight. We will continue on and finish up alkynes next Tuesday. and then move into the last chapter of the class, which is alcohol. All right. So I will see you over in, actually, might be easier just to stay in here. So we're just going to be going over the homework. So it's probably more comfortable for y'all to sit in here than it is to go sit on lab stools. So why don't we just take a 10-minute break, come back in here and go over the homework.